Have you ever been on a road trip and come across those incredible electrical posts with lines of wires complementing the stunning horizon in the middle of your journey? If that's the case, you probably started thinking how we get energy to fuel everything from our homes to devices. Or maybe it has to be due to those long wires. But exactly what are they and what are their functions? You started searching through science books in the hopes of finding the answer you were looking for. No, you don't have any books on that topic. You did some research and you've actually found it. Yes, transmission lines. How come this thing intrigues me when I feel too lazy and dumb to think of anything right now? It's true that a famous philosopher, I forgot the name again. A prominent philosopher once claimed that the human mind has always been curious. With one question comes another and another and another until you can't think straight any longer and just want to sleep. But you can't because your mind is fighting an internal battle. So you turned into a zombie, a true human zombie who lacks adequate sleep and functions like zombie. You became more interested, curious to learn more. A single query produced by the human mind developed more queries. It is necessary to state the fact that the more you learn, the more you know how incredibly dumb you are. Oh my goodness, I've already said a lot of things without giving a proper introduction. Hello everyone, I am Shina Joy Pipingoy, a BS ECE3A student who will provide you with knowledge about transmission lines. Well, relax and be with me as we go along this journey of unlocking some gist through transmission lines. So, are you ready? Transmission lines are important components of an equipment and is vital in the transmission media since they carry information, electrical power, and energy. Wire or transmission line, what's the difference between the two? A wire is said to be a single conductor, while a transmission line is composed of a pair of conductors or any medium carrying information. In other words, it is consists of at least two wires. Here is the fundamental principle of the transmission line. It connects different circuit elements. Next, parasitic resistance, capacitance, and inductance are all present. Next, we have the equivalent circuit of a transmission line. Here is the corresponding circuit diagram of a transmission line. The two conducting wires of a certain length and the transmission line's parameters are distributed over its entire length. These are the R, L, C, and G parameters, which we will go through in the next section. Due to their isolation, two conducting wires have some capacitance. However, since this dielectric medium is not fully insulated, some leakage current passes through it. Transmission line includes telephone lines, power supply lines, to name a few, cellular stations, telephone, Wi-Fi, radar, submarine communications, television, circuit boards, computer networks, and microchip interconnections all make use of transmission lines. Next, we have the types of transmission line. Transmission lines are majorly classified into the following categories. First, we have the coaxial lines, which fall under multi-conductor lines that are commonly used for high-frequency applications. It is made up of an inner conductor surrounded by concentric cylindrical insulating material. These transmission lines are often used in applications requiring high voltage levels. Next is the open wire line. Two lines or wires are separated by a dielectric medium in an open wire transmission line, with one end attached to the source and the other to the destination. They are claimed to be the cheapest and the easiest form of transmission line, and the biggest downside is higher cost for installation and maintenance. Next are waveguides. For signal transmission at microwave frequencies, this category of the transmission line is used. As they are hollow conducting tubes, they look a bit like a coaxial cable line because they do not have an inner or center conductor as present in coaxial cables. There are also those rectangular waveguides. Next, we have the microstrip line. It is a simpler structure than strip lines that separates the signal conductor and ground plane with a dielectric layer that allows fabrication of any technology. Lastly, we have the fiber optic cable. Fiber optic cable is a type of a network cable that is made up of strands of glass fibers that are enclosed in an insulated casing. They are made for long-distance, high-performance data networking and telecommunications applications. Fiber optic cables also have a higher bandwidth than wired cables and can relay data over longer distances. Next is the parameters of the transmission line. It is important to have an understanding of the parameters associated with signal transmission through a conductor. So in general, there are 4 parameters associated with the transmission line. First, we have the resistance. The cross-sectional area of the conducting material determines this parameter of any transmission line. These are distributed parameter networks, which means that their parameters are distributed uniformly over their entire range, as we have already mentioned. The resistance of a transmission line is equal to the rho times the length divided by the area. Here, rho is the conductivity of the conducting material, L is the length of the transmission line, and A is the cross-sectional area of the line. Its unit is ohms per unit conductor length. Next, we have the capacitance. The transmission line is made up of 2 parallel conducting wires separated by dielectric material, as we have already mentioned. As a result, it acts like a parallel plate capacitor. As a consequence, it has some capacitance that is distributed evenly over its length. It is expressed in farads per unit conductor length. Next, we have the inductance. Current flowing through the conductor determines its value. Inductance is represented by L, and its unit is Henry per unit length of the conductor. Lastly, we have the conductance. It is mainly located between the 2 conducting wires and is denoted by the letter G. The unit of measurement is mho per unit length of the conductor. We have here the line constants. There are 2 types of line constants. First, we have the primary line constants. The primary line constants are parameters that describe the characteristics of conductive transmission line in terms of the physical and electrical properties of the line. Resistance, conductance, inductance, and capacitance are examples of primary line constant parameters. Next is the secondary line constants. The secondary line constants can be used, for instance, to compare the characteristics of a waveguide to a copper line, whereas the primary constants have no meaning for a waveguide. Characteristic impedance, attenuation constant, phase constant, and propagation constants are all secondary line constant parameters. Next, we have the reflection coefficient. It is a vector parameter that describes how much of an electromagnetic wave is reflected by an impedance discontinuity in the transmission medium. It is equal to the ratio of the amplitude of the reflective wave to the incident wave expressed as a source. So the formula for finding our reflection coefficient is this, where VR is our reflected voltage expressed in phasor and VI is the incident voltage expressed in phasor. We also have another formula for finding our reflection coefficient, denoted by the one at the very bottom. Next is the velocity of light. The velocity of light is only a function of the absolute permeability and absolute permittivity of the medium. It is given by this formula: velocity of light equals 1 over square root of permeability of free space in vacuum times permittivity of free space in vacuum. It is equal to 2.9979 times 10 raised to 8 meters per second in free space or vacuum. Let us also take note of these following constant values and their specific unit of measurement, as we will be dealing with them in the long run. Next is this formula. Relative permeability of the line is equal to the absolute permeability of the line divided by the permeability of free space in vacuum. The last one is relative permittivity of the line equals absolute permittivity of the line divided by the permittivity of free space in vacuum. If not specified in the problem, we will assume that the velocity of light is equal to 3 times 10 raised to 8 meter per second. Next, we have the velocity factor or VF. The velocity factor is the ratio of the velocity of propagation of a signal in a transmission line to the velocity of light in free space. It is given by this formula. Also, the velocity factor is equal to 1 divided by square root of the relative permeability of the line times the relative permittivity of the line. And most medium have the relative permeability of line equals 1. Also, the velocity factor is equal to 1 divided by square root of the relative permittivity, or equal to 1 divided by the square root of dielectric constant. Remember that the velocity factor in free space is always equal to 1. Next, we have the velocity of propagation. The velocity of propagation of a signal in a transmission line is the speed at which the electromagnetic energy travels inside the line. In most cases, it is equal to the phase velocity, but not all the times. We have several ways to find the velocity of propagation. Here are the formulas. Next, we have the propagation constant. The propagation constant is the secondary line constant. It is the measure of the change undergone by the amplitude of the wave as it is propagates in a given direction. So the formula for finding the propagation constant is this. Propagation constant equals square root of quantity R plus J omega L. The L is the inductance, Chi, the conductance, plus J omega C, which is the capacitance. It is also equal to the attenuation constant plus J phase constant. This variable, which is also called the attenuation constant, is the real part of the propagation constant. It also represents the rate of decay of the wave as it travels down the transmission line. It also defines the rate of reduction in space of the wave amplitude. It is measured in Nepper per meter or decibel per meter, and 1 Nepper is equal to 8.686 decibel. And the last variable is the phase constant. It is the imaginary part of the propagation constant. The phase constant is calculated exactly the same from capacitance and inductance per unit length. It is measured in rad per meter or degree per meter. Next, we have the wavelength. Frequency doesn't change when a signal encounters a different material, but due to transmission line effects, the wavelength changes. The change in wavelength compared to free space is inversely proportional to velocity factor. So here we have the different formulas in finding for the wavelength. Remember that the formula we use in a transmission line is different from the formula we use in free space in finding for the wavelength. First idea that we have to remember, the effect of a transmission line on a device is determined by its length in relation to the wavelength of the signal traveling through it. In conclusion, transmission lines are important components in both electrical and electronics fields since they are used to transmit high voltage electricity over long distances that links electricity generators to consumers. So, as we can see, collecting knowledge and immersing ourselves in all of it help us understand how things work and all the principles that underpin them. Of course, there will be lots of formulas and equations to encounter, but bear in mind that they aren't just numbers, they are also insight. I hope that you've learned something in my presentation, although it's just a short one, because it's just a simple gist about transmission line, and you will have more about it in the long run. Let's all keep learning together. All the best. I'll see you later. Bye.